Okay. Good afternoon, everyone. I hope you're doing great. Today, we're gonna dive deep inside the ConvNet concept. We said that convolutional neural nets actually is a kind of complicated version of artificial neural nets, but we use the word interchangeably. That was not very much accurate, but today we are gonna focus on ConvNet, the architecture, how it works, and we answer many of the challenges that we could face. So as we said, ConvNets are very much useful in image classification problems. Also, we said that, and previously what we worked was densely connected network, and we achieved something like 97.8 as the accuracy after, I don't know, 20, 30 bucks. But let's see if conv2D and convolutional neural nets can give us any better result. Surprisingly, just after 5 epochs, not more, it reaches to something like 99% of accuracy. And it shows that how amazingly the performance increased using the ConvNet. We have two major layers. One of them is conv2D and the other one is max pooling. And yesterday we just announced them, but today we are going to see how they work and how they impact. And the very first thing that we saw was the first layer of conv2D that receives the input, which contains 28 by 28 pixels. It was the widths and heights, right? And what is the one at the end? Anyone remembers? The color channel, right? Because it was black and white, we had one here. But if you see, we have a number here, which is 32. 32 is the number of channels in the conv2D. But we only have red, green, blue. So what is that 32? If anyone can have any guess. Look at this one. After creating some conv2D max pooling, conv2D max pooling, conv2D, we get to a place, if you say that, show me the model, it's going to tell you, okay, the very first convolutional neural nets output would be 26, 26. Guys, is it a kind of random number because it was 28? We just randomly say, let's just say 28 minus 2, or it has come from somewhere. What is your opinion? Okay, let's see. And we have max pooling. The name is self-descriptive. It's going to pull, it's going to fetch the maximum value in a window of 2 by 2 cells. Means that out of 4 different values, we are going to fetch the maximum number, right? And what is the relationship between this one and this one? Again, we have 13, 13 minus 2, 11. You see that? Divided by 2, the floor of it. It's going to give us 5. And then minus 2 again, because of conv2D, is going to be. Do you see that kind of pattern here? So we started with 28, end up having 3 by 3. So 28 by 28. If I want to show you. Pardon me?
28 and 28 is like 50.
Yep. So it is something like 28 by 28, something like this. And the next layer is going to be 26 by 26, right? And the next layer all the way to what? To a place that it's going to be 3 by 3, right? But what is the depth of that layer? So it's not going to be something like just 3 layers that we had here, right? It's going to be something like 64 layers. Does that make sense? And definitely it's not going to be like red, green, blue if the first layer had 3 channels. This is going to be 64 channels. But what are those channels in convolutional neural nets? We are going to see them. It's
None. So what is that? Yeah.
Okay. There are some parameters that are optional, and we are going to talk about them in 5-6 pages from now. Okay, just stay tuned. We're going to talk about all. Look at this one. One of the things that it mentions here is output of every conv 2D and max pooling layer is a 3D tensor of shape that we have height, width, and channels. But I asked you that it cannot be red, green, blue. So it is something different. And the numbers are, as you see in here, are not any number that are familiar. But what are they? It mentioned that the next step is to fit the last output tensor of shape 3, 3, 6. We have, guys, something that started with 28 by 28 and 3. Then this, then all the way to 3, 3, 64. After that, we are gonna use traditional form of densely connected layers, like what we learned in chapter 1 all the way to chapter 4. Does that make sense? So we're gonna just, it's like something like a hat, we are gonna put it on top of the head of convolution, the densely layered network that we learned. And this is the place that we use 64 and then activation ReLU, and then we say 10 and softmax. Look at the summary of everything that we have. You see in the last layer, it says 10. And the thing is, right now, I just defined the layers. For creating a model, we need a few more parameters to have. What are they? To create a model, we need a few more things. First, we need to know that it's sequential, not functional. The other thing is we need to flatten. The best is to not only flatten, but also normalize. We didn't do that here. The other thing that we need to do is, guys, we load the data set and this data set, and then here we are gonna start, doing those things like reshaping. Instead of saying 28 by, 28, we're gonna say 28 times 28, right? And then we divide them by 255, and we change the output to categorical. We know all of those things. And now this is the major part. A compile technically is defining all those parameters like the optimizer, loss function, and accuracy. If you don't mention metric, a default value is accuracy as well. And then look at this. The epoch number is not something crazy like what we had before, like 20, 30, just we have 5. And the back size 64. Let's see what is the accuracy, guys. Isn't it crazy? 99. You might say, okay, we want to try it. I told the friends, if you go to the course content, you're gonna see here the last folder for those who arrived later. We have chapter 5. So please download that and drag and drop it to Colab. And then let's do it together. So run all these. You see that this is the train part, and it takes a few seconds. Just look at this one. The accuracy, even in the first epoch, is something crazy. It's like almost 95%. And epoch number 5, it is pretty close to 100. You might say that, okay, so this is just a training, and training could be 100, but how about the test? Look at the test. I'm sorry, I don't know why I just ran that 2 times. But the numbers are pretty similar to what we had before. So the funny part is, if you check the test, guys, what is the test accuracy that you achieved? For me, it is like 99.31 or 0.9930. Compared to this, the overfitting is negligible. It's like 0.004. So not only we had higher accuracy, but also we achieved lower overfitting. But how this magic happens? To understand the reason of that amazing result, we need to know the architecture of convolutional neural nets. If I want to summarize in one sentence that the benefit of using convolutional neural nets compared to densely layered of artificial neural nets would be these 2 sentences. It says that densely layers learn global pattern in their input feature space, whereas convolution layers learn local patterns. What does it mean? Let's go to this example. Guys, if you have a scanned digit and number 6 is something like this in here, and you have another one which has almost similar number, similar shape, but it's in the other portion of the screen, there's a big chance that the system cannot assign a proper label for it. And the reason is it knows a global number 6 if it is in the same position. The good thing about neural net is it's going to say, okay, I have some filters. One filter, I'm going to recognize the diagonal lines. In one, I'm going to recognize the curves, for example. In one, I'm going to recognize the vertical. In the other one, I'm going to recognize the horizontal lines. And listen to this part. Wherever I can find any of these samples, no matter if it is in this part of the screen or in this part of the screen, do I have the same pattern? So because I can find these kind of things, no matter which part of the screen they are, so you see that the convolution layer learns local patterns, right? Means that if any, it's like saying that wherever you can find a picture that contains ear, nose, lips, then that's a picture of a human. No matter if the head is tilted or if the person 90-degree, looks at the camera, something like that. So look at this one. It says that 3 by 3 part of the formula talks about this. I'm gonna fetch one portion and I say, okay, if I can find this and this and this in one number, we are talking about number 4, that kind of thing. Okay. Look at this. It says that this key characteristic that we just concern about the local features, not just the global image, because the global image needs, for instance, number 6 should be centered. It should be almost the same size. So these characteristics that achieved by convnets bring us 2 properties. One is the pattern they learn are, guys, this word, translation invariant. What is the meaning of translation invariant? Translation invariant means that if I open a door and the cat comes just looking at it in the class with the head 90-degree tilted, that's a cat, right? So wherever you can find those 2 ears, lips, mustache of cat, and so on, you're gonna say, okay, that's cat, no matter if the head is in this angle or in this angle. So that is what we call it, translation invariant. So translation invariant means that's what our eyes do all the time. No matter if I look at Mahir from this angle or from this angle, I can recognize Mahir, right? This is the real world. And that is why it says that the convnet can recognize it anywhere. And a densely connected network would have to learn the pattern on you if it appears at a new location. Means that if I see Mahir on TTC, I cannot recognize if I just use just normal densely connected layers, right? It should be in the same frame, the same position. It says that this makes convnet data efficient when processing images because the visual world is fundamentally translation invariant. So guys, spend just 30 seconds. Explain to your friend if you want and say why it says that. I already gave you 2 examples, cat and Mahir on TTC, but you just find it in your own words. What does it mean when it says because visual world is fundamentally translation invariant? So the next part is it says that they can learn the spatial hierarchy of patterns. What does it mean, a spatial hierarchy of patterns? For instance, in the first layer, guys, we are talking about those channels. Let me just reveal one thing. Those channels are nothing but filters. So when we say 32, they are not channels of colors, they are channels of filters. So a first convolution layer will learn small local patterns such as edges. A second convolution layer will learn larger patterns made of the features of the first layer. Increasingly complex and abstract visual concepts would be learned. And because the visual world is fundamentally spatial hierarchical, means what? What is this page? To return past 123. Okay. Look at this one. Imagine that we have a picture of a cat like this. Guys, it's way ahead of this session, but it's going to give us good understanding. Now here, what is this? It's kind of, just imagine that we have a cat, the poor cat, we have a sieve here, the cat out of passing that filter, right? But we should ask the cat to pass 64 filters or 32 filters. Look at this is another filter for the cat, okay? You might say, what are you talking about? Look, we apply the filters, the very first layer, 1, 2, and this is 16, 32, guys, except these are 32 filters. For the first one, we get, you see, for instance, very sharp edges, and so on and so forth. In the next one, we are going to get more abstract lines, like we can just recognize eyes here, can have, right, more of ears here. And this is the next layer, and this is finally the last layer. Guys, do you see that we are talking about ears in general? We are talking about combination of ears and eyes, right? And you might say that, hey, why in that case we do not have any result in these parts? Guys, imagine that we have sieves, and the sieves in the first layer, they are coarse granularity, if I'm pronouncing it correctly, means that they are quite big, so everything could pass through the first layer. But we are going to have finer sieve for the next layer, and finer, so many things could not pass through those layers. Does that make sense? Stefan, does that make sense? So first, I can have something out of this filter because they're quite big. And for the next one, it's going to be a little bit finer, smaller. And then for this one, we could have lots of things that they cannot go through the sieve. You might say, okay, what kind of filters we could have? And look at this one, guys. All of us either have bicycle or we have seen at least bicycle. So this is a kind of bicycle, right? But if I ask you to, okay, draw a bicycle, somebody could draw something like this, somebody could draw something like this. We want to say one thing. Computer does similar job, means that if I can recognize a very high level, kind of just something like wheel, something like saddle, right, the seat or the handles, then I can say that should be bicycle. Means if I can have a very high level of these things like eyes, ears, no matter where they are, how they are, they should be cats. Does that make sense? Kind of. But look at the next filter shape. The very first layer, we have simple filters. Guys, they are simple filters. If you pass something through this one, I'm talking exactly this one. What would be the output? Just vertical lines, right? What would be the output of this one? Obvious. Sorry, this one was diagonal. This one is vertical. And we could have filters that they take care of the curves and so on. But look at the next layer. It is a little bit more complex, the filters that we have in that layer. And then we are going to have more complex, and then it's a kind of hierarchy. We get more complex features. So not everything could pass through these complex features. Does that make sense, guys? Right? That's exactly the assignment number 3. So that's why today, actually, I want to tell you whatever we need to have to start and complete assignment number 3. So if I'm not mistaken, I was here. I told you the first one, and the second one, it says that a first convolution layer will learn some local patterns such as edges. A second convolution layer will learn larger patterns made of the features of the first layers. And then it says that increasingly complex and abstract visual concepts, which could not be applied to all the part of the image, right? So look at this. Here I have a picture. I can filter out some things like, I mean, these curves and mustache here. And when I go to the next layer, it's going to be more abstract. So I can combine these and say that if I can find these things somewhere, probably it should be ear, an ear of cat, or this is the mustache of cat, and something this is, it could be an eye of cat.
Like just show us. Is there any library or something like that, right?
In 5 pages, we are going to get to that, but let me just give you a quick answer. It's going to be a random filter. Imagine that you go to Canadian Tire and you pick one of the toolboxes that they have screwdrivers, right? You have 32 different screwdrivers there, and there's another box over there too. So the size and the type of the screwdrivers are not exactly the same, but they are in the same range. You know what I'm saying? It's exactly like that. Does that make sense? So just accept that as a kind of quick answer, but we are gonna go, I promise, deeper into that concept. There's one thing. The first thing that we have is a feature map, whatever it is. For instance, you have a picture of a cat. That's a feature map. And what you get out of it is going to be output feature map. So this is going to be a feature map, and this is going to be output feature map. This one is going to be feature map for the next layer, and next layer would be the output feature map. So it's kind of hierarchy, and we're going to get to that. Look at this. It says that convolutions operate over 3D tensors called feature maps. You remember the first one was 28 by 28 and 1 dimension of 1 color with 2 spatial axes, height and width, as well as a depth axis, which also called channel. But for the first one, because it is RGB, we have 3, but the convolution operation extracts patches from its input feature map and applies the same transformation to all of these patches, producing an output feature maps. Because we don't have that number 3, so it's not going to be something like RGB. We have something different, and those channels are filters, like sieve, but different shape of sieves, right? And this is the time that we watched the very first video that I have provided here.
Convolutional networks, or ConvNets. ConvNets are neural networks that share their parameters across space. Imagine you have an image. It can be represented as a flat pancake. It has a width, a height, and because you typically have red, green, and blue channels, it also has a depth. In this instance, depth is 3. That's your input. Now imagine taking a small patch of this image and running a tiny neural network on it. We say K outputs. Let's represent those outputs vertically in a tiny column like this. Now let's slide that little neural network across the image without changing the weights. Just slide across and vertically like we're painting it with a brush. On the output, we've drawn another image. It's got a different width, a different height, and more importantly, it's got a different depth. Instead of just RG and B, now you have an output that's got many color channels, K of them. This operation is called a convolution. If your patch size were the size of the whole image, it would be no different than a regular layer of a neural network. But because we have this small patch instead, we have many fewer weights, and they are shared across space. A ConvNet is going to basically be a deep network where instead of having stacks of matrix multiply layers, we're going to have stacks of convolutions. The general idea is that they will form a pyramid. At the bottom, you have this big image that's very shallow, just R, G, and B. You're going to apply convolutions that are going to progressively squeeze the spatial dimensions while increasing the depth, which corresponds roughly to the semantic complexity of your representation. At the top, you can put your classifier. You have a representation where all the spatial information has been squeezed out and only parameters that map to content of the image remain. So that's the general idea. If you're going to implement this, there are lots of little details to get right and a fair bit of lingo to get used to. You've got the concept of patch and depth. Patches are sometimes called kernels. Each pancake in your stack is called a feature map. Here you're mapping 3 feature maps to k feature maps. Another term that you need to know is stride. It's the number of pixels that you're shifting each time you move your filter. Stride of 1 makes the output roughly the same size as the input. A stride of 2 means it's about half the size. I say roughly because it depends a bit about what you do at the edge of your image. Either you don't go past the edge, and it's often called valid padding as a shortcut, or you go off the edge and pad with zeros in such a way that the output map size is exactly the same size as the input map. That is
we heard a few things here. One of them was a stride, and the other one is valid and same for padding. Partially they are answering your question, but it is super shallow. Just quickly saying, but we are gonna see the better definition of these things.
often called same padding as a shortcut.
So let's just dive deeper into okay. Dive deeper into one.
You can
Sorry.
tell us.
I'm sorry. To one example that I'm going to talk. Okay. That's surprising. In the previous, let's just get on to the out. Okay, there we go. So we have something like this, and I'm going to take a snapshot from this picture because people cannot see the whiteboard here. The best is to use exactly this one. And there we go. Did you hear about conv to the 3x3 that the gentleman said? It means that we are going to go through, guys, 1, 2, 3, and 1, 2, 3. So we are going to have a frame like this. Right? We fetch the numbers from that, and we have a filter. And again, that filter is something like this, just a number like 0, 1, 0, 5, 2, 2, 0, 1, 0, something like this. We are gonna multiply the numbers in that and bring it exactly, boil it down and add them all. For this, because they are all zeros, it's gonna be 0, but it's going to shape the first element of that. Then we are gonna move, look at this one. We slide towards right, 1 block, 1 column, and that is what we call it the stride equal to 1. We go 1 by 1. We do the same thing and it shapes the value of here. Does that make sense? The answer to that question is this one. What is that? This is that. Look at this. Here it is. No, we have different names for that, but guys, for a few seconds, just look at that, what is happening. You ask very advanced questions. Kind of random. I told you the randomness comes from that you go and you pick that toolbox or that toolbox, but they're in the same range. You might say, Reza, I was not convinced. Tell me. Very simple. Type kernel matrix wiki and go to the second thing. You see that when you apply this one, it's going to sharpen the image like this. If you use this one, it's going to just intensify on these lines. You see that? And if you use this one, it's going to make it very sharp. This one is going to make it very blur. Right? Toolbox. So you pick this filter, you pick that filter. We have lots of filters. And one of the things is we need to find, when I say we, here I'm talking on behalf of a deep learning algorithm. We need to find which set of filters work the best. And I'm going to pick those, right? But look at this one, guys. Isn't it familiar for you? These kind of filters? Where did you use them? Yeah, Facebook, Instagram, right? In any place, guys, these are nothing but the filters that, and those very much sophisticated filters that we say, wow, what a filter. They're nothing but just adding a few of them together. And the thing that we have in assignment 3 is just knowing more about this, doing a little bit of calculations, and what is already coded and Kiara's provided for us, we just want to know that's not a kind of magic. We can just do it ourselves too. And let's go a little bit further. It says that, okay, so we understood there are filters, and filters encode specific aspects of the input data. When it says specific means, for instance, vertical line, horizontal line, the color, sharpening the picture, and so on. A single filter could encode the concept presence of a face in the input. For example, in the MNIST example, the first convolution layer takes a feature map of size 28 by 28 and 1 channel. This is super important. And then it's going to convert that to a picture of 26 by 26. And you might say, why always it just drops the size? It's like 28 minus 20 or minus 2. And what is this? Now we know that it's like having 32 different pictures after the filters, right? We created 32 different pictures. So it computes 32 filters over its input. Each of these 32 output channels contains a 26 by 26 grid of values. which is a response map. So what you get is a response map based on the original picture. So we have one picture, we have 32 different response maps. That is what the term feature map means. Every dimensions in the depth axis is a feature or filter. This is the emphasis of using filter instead of feature map. And the 2D tensor output would be something like this. Whatever the size is, we have, for instance, 32, 64, or whatever feature maps. The thing is, look at this one. Imagine that for now, just think that, again, I'm going to give this O to this filter, and I say, wherever you can find this diagonal lines, just intensify them. This is going to intensify this part, right? And this part. This is going to be 1. What about if I just have exactly opposite? So it's going to intensify this part and this part. Totally opposite, right? What if I have something like, and we are going to see in one of the videos that it exactly says how it's going to work on that. Maybe you want to just see the outer layer of it. Maybe you want to see the inner side of it, right? So they should be different filters for that. It says that convolutions are defined by 2 key parameters. One of them is size of the patches extracted from the input. It says that 3 by 3 or 5 by 5. I rarely saw that any size but 3 by 4. So we mostly use 3 by 3. And this is the reason why we have 28 as the input, but we have 26 as the output. The other thing that we want to know is the depth of the output feature maps. What's the meaning of depths? It was colors at the beginning, but next step is going to convert to what? Exactly, number of filters. So that is why at the end it says that, for instance, the depth of 32 and ended with a depth of 64. This paragraph is super important, so I read it, and we are going to watch 2 things together. And one is, it says that in Keras conv 2D layers, the parameters are the first arguments passed to the layer, which is going to be the number of channels and then heights and widths. A convolution works by slicing these windows of size 3 by 3 or 5 by 5. Guys, remember that I showed you this example and I said we are going to pick 3 by 3. So what if I choose 5 by 5? Not a problem. It does something similar, but most of the time we just use that 3 by 3. And stopping at every this is kind of confusing. Stopping at every possible location means go to this one, then go to the next one, then go to means stop, do the calculation, go to the next, do the calculations, go to the next, and so on. And extracting the 3D patch of surrounding features. So each such 3D patch is then transformed. What's the meaning of transformed? Into a 1D vector of shape. All of these vectors are then spatially assembled into a 3D output map of the shape that contains height and widths. But let me tell you one thing. If you go to one of those police stations, they have a picture of criminals, for example, and they say, okay, if the person shaved, they could just look like that, like this, and if they have artificial beards or mustache or something. So you see, there are several pictures of the same person. Filters are doing something similar. The difference is it's going to zoom to one specific part. It says that if, for instance, the nose of that person is big, so that person could be Reza, right? Or for instance, the ears are pointy, so that person is Reza. So it filters, it goes through the, what do we call it? The specific part of the picture and zoom there and just fetch the outputs like that. So every spatial location in the output feature map corresponds to the same location in the input feature map. For instance, with 3x3 windows, the vector would be, what is this? If we go to a position I and j, we start from, look at this example. If we have a result in I, for instance, this is row number I and column number j. This is the result of something here, which starts from I minus 1, I and I plus 1, j minus 1, j and j plus 1, right? So the result of this 3x3 would come into this j and I. It wants to tell you that. Okay, again, look at this thing.
It's like auto generated.
For just for the sake of now, imagine that somebody gave us that, a cheat sheet, said that, okay, don't tell anybody, this is your kernel matrix, go and have fun with it, okay? So you have this one from as a cheat sheet. We don't know where it has come from, but look at the mechanism that it works. Do you see those kind of numbers, brown, red things? Look at this one, 0, -1, 0, -1, 5, -1, 0, -1, 0. You see that? These are just these numbers. Huh? And look at these numbers, 100 to multiply with 0, 100 multiplied by 81, and so on. At the end, just sum them up. It's going to give you this number. Place it there. So, guys, this is something like this. Does that make sense? So what is the number of a stride? Whenever we say nothing, it's going to be 1 by default. Your question. So here, guys, it is 3x3, right? Let's go and look at it. Just one stride at a time, one column at a time. But what if we go 2 steps? Then a stride would be 2. Okay. This is another serious question. And if you don't mind, I'm gonna answer that. One of the things that we use a stride is to downsampling, to reduce the size. But that is not recommended. And the reason for that, we are gonna learn it in 2 pages from now. Okay, let's go to the next part. By saying that, we are gonna watch the other video that I've provided, actually based on the things. I'm not sure 3 first, or let's just watch this one. I very much like everything about his presentation.
Well, I would understand being perhaps slightly different from what people would use Instagram as a filter. Usually in an app or phone app or Facebook or some other thing where you can apply some filter, it's going to actually be a combination of lots of low-level processing of various types, blurs, contrast changes, color changes. What I tend to use in my day-to-day work is the low-level Gaussian blurs, edge detection, this kind of stuff. But really, they're all filters, so they all take some image, focus it, and come up with some out. Today, we're going to look at a simple technique called kernel convolution. And that is kind of a core of Gaussian blurs and mean blurs and edge detection and lots of other techniques. And it's a very simple technique that we use a lot around here with computer vision work. Kernel convolution is just a process where we take a small grid of numbers and we pass them over the whole image, transforming it based on what this numbers are. And by using different numbers in the kernel, we can form blurs or edge detection or sharpen, unsharpen, basically any of that. So I'll first describe kernel convolution and then we'll look at a couple of examples of what sort of kernels we see on top. Kernel convolution works by, if this is our test image, that's 5 by 5, and this is our kernel, which is 3 by 3. Generally speaking, the kernel will be smaller than the image, and usually actually quite small. And what we do, this is my movable kernel we've come up with. What we do basically is for every pixel in our image, we put our kernel over it so that the pixel is in the center. So let's look at this pixel here, number 64. We put our kernel over it, and then we are looking at the 3 by 3 grid centered around that pixel. And we take whatever values in our kernel, multiplied by 17, and then the top value multiplied by 14, and the top corner value multiplied by 13. So we take each corresponding image value and kernel value, we multiply them together in pairs, and then we sum the whole thing up. And then finally, we normalize by dividing by the total value of our kernel to make sure that it doesn't get right all the time.
That's a bit like averaging.
It's exactly, it is averaging, yeah. In a way, it's just a big weighted average, or if all the numbers are the same, an actual average. So, in fact, that's the first one we can look at.
So look at this one. The gentleman said after just doing the multiplication. So imagine the range of the numbers is something like between 0 to 255. I'm just fabricating. If you just use the blur matrix, and I'm gonna show you the blur matrix, which is this one, right? The problem that is gonna occur if I don't divide it by 9, then it's gonna get very much darker. Does that make sense? The range would be something between 0 to 255 times 9. So that's why it's the gentleman said that we would be better off dividing by the number of elements in the kernel. In this example is 9. So is it necessary? No. In many cases, you can just, live with the just matrix multiplication.
In our kernel 1, then that's a mean blur. So if you go into Photoshop or any other image processing package and you go for blurs, blur filters, and mean, that's what it's going to be doing. This is a kernel of size 3. You usually do it obviously centered around single pixels, so odd size, so 3, 5, 7, so on. So what we're going to do here is we're going to go 17 multiplied by 1 plus 14 multiplied by 1, so on, and divide the whole thing by the sum of this, which is 9, and that will basically take an average. And then we'll overwrite that pixel with the output of that kernel convolution. The only thing.
Just did you see that the gentleman, after doing the calculations and having the number, and after dividing by 9, then brought that value
With the output.
into this position? Why not in here? That's the question, right? So I'm gonna answer that, but before getting any further, this is where I want to stop this video. So the rest would be kind of repeating these things in many other filters. They're different, just filters. But before I continue, I want to tell you today's session would be like that. I'm going to go through just a few pages of the book, but we watched lots of things. Some of them are reviewing from day 1. There's this one video that we watched 22 minutes of it out of 30 some. And that 22 is gonna start from day 1 of our session. It's like compressed version, a review of everything. And it brought us to, it is going to bring us to the convolutional neural nets and talks about all the aspects. Why I'm saying that, because it could be a little bit boring for some people to watch and just see what we are gonna pause and talk about it. And the good thing about today's the videos and all the contents that we cover is you're gonna get over 60% of the answers for the assignments. That's the intention. And apart from it, we're gonna watch one video at the end, and that's the last video, video number 9, which a gentleman from MIT, Alexander is his name, Alexander Amini. He's just amazing, and he's talking to people in MIT University, teaching the same concept. And I want you to just listen to that and see almost everything is familiar. And you can just simply follow the content. Okay? By saying that, now it is 1:05. Let's have a 10-minute break. I'm going to take care of the attendance. So if anybody thinks that it's not going to be useful, you're going to have your attendance. By all means, you're more than welcome to continue, or you can just, yeah. I'm sorry. That one. Stefan, just give me a second. Okay, you are. Sorry, number? Do you know the number? What's your name? Opinion. Okay. Opinion, right? Okay, thank you. And I think so. It's gonna be. Think so. Yeah. Okay, thank you. Thank you. No worries. And let me. Yeah, yes, inflation. Sorry. Other than some. Joe. Okay. So we are about to start. Is it? Yes, it's the time. The other thing that I thought would be very much useful to watch and to enjoy. Hey guys, do you see this thing? Till this moment, we just work on something like 3x3 window, and then this is going to get the internal, this part, and then it's going to get this part, and it's going to get bigger in terms of the number of samples that we have, the result of the filters, right? So it's going to be something like a pyramid. And I told you in here, yes.
Is it image right? Didn't you say like it's gonna go on like each column? And there are only like three. So is that right? Or
Yeah. No. We just wanted to say, okay, let's pick just one 3x3 of it, not the whole picture. So it's like out of 28x28, for example, let's focus on the window of 3x3 and see what's going to happen in the next level and the next level and the next level. Let's watch this one. It gives better definition. That's video number 3. And don't worry, you're going to have lots of awesome videos to, you know, this gentleman.
Hi, and welcome to episode 3 of Zero to Ill TensorFlow. In the previous episode, you saw how to do basic computer vision using a deep neural network and match the pixels of an image to a label. So an image like this was matched to a numeric label that represented it, like this. But there was a limitation to that. The image you were looking at had to have the subject centered in it, and it had to be the only thing in the image. So the code you wrote would work for that shoe. But what about these? It wouldn't be able to identify all of them because it's not trained to do so. For that, we have to use something called a convolutional neural network, which works a little differently than what you've just seen. The idea behind a convolutional neural network is that you filter the images before training the deep neural network. After filtering the images, features within the images could then come to the forefront, and you would then spot those features to identify something. A filter is simply a set of multipliers. So for example,
Filter is simply a set of multipliers, right? Answer to one of the questions. Filters are simply a bunch of multipliers.
if you're looking at a particular pixel that has the value 192, and the filter is the values in the red box, then you multiply 192 by 4.5, and each of its neighbors by the respective value. So its neighbor above and to the left is 0, so you multiply that by -1. Its upper neighbor is 64, so you multiply that by 0, and so on. Sum up the result, and you get the new value for the pixel. Now this might seem a little odd, but check out the results for some filters, like this.
Okay, what is the result of that? When you apply this, you see, you just tell me. Okay, exactly. The vertical lines are more visible, right?
That when multiplied over the contents of the image, it removes almost everything except the vertical lines. And this one, that removes almost everything except the horizontal lines. This can then be combined with something called pooling, which groups up the pixels in the image and filters them down to subsets. Okay,
we talked about till this moment conv2D parts. We didn't talk about max pooling. So let's see what is the role of max pooling. Guys, if we keep moving using convolutional neural nets, because of number of filters that we are going to use, it's going to drastically increase the size of the samples that we have, right? So we had one picture at the beginning, then we said, okay, how about having 32 pictures, almost the same size? And then if we don't have any max pooling, we're gonna say, how about having 64 pictures from the 32, means pick any one of those pictures and apply 32 on top of it. You know what I'm saying? Pick one of those 32 and now apply. So it's gonna be crazy. We are gonna exactly see what is the role of max pooling. If you don't have that, we have two problems. We cannot see the, I'm gonna answer you quickly, but let's watch it in the video as well. We are gonna get two benefits out of it. Whatever the feature is and you want to intensify that, like vertical lines, horizontal lines, it's gonna intensify those features, make them more visible. That's the first thing. Secondly, they are gonna drastically reduce the size, which unnecessary. You don't want to have a masterpiece in art having those pictures. You just want to simply say, okay, if this is cat or dog, for example, right? So we need to reduce the size to make it reasonable to be handled by the processor. Let's see.
So for example, max pooling 2 by 2 will group the image into sets of 2 by 2 pixels and simply pick the largest. The image will be reduced to.
Look at this one, please. Do I have any? Okay, do you see that we have 2 by 2 here, 0, 64, 48, 192? This one, what is the maximum number in this? 192, and we are gonna have that. So instead of having 2 by 2, we just have one value. Is it going to be a stride equal to 1 negative right here? The next one is 128, 28, 148. Excellent. We are gonna have strides too. We don't go from here to here, right? We go 2 columns towards right. So stripe is what? 2. And then we are not going to go to the next line after we finish this row. We go 2 lines below that. So there is no overlap. Do you see that? So 142, 226, and 255. The question that you asked that, okay, are we going to use a stride? Yes or no? So what is the benefit? It has benefit, but because we are talking about the major picture, if you just use the stride equal to 2, you're gonna unintentionally, you're gonna lose some of the things that they could contain the maximum values. This is more reasonable. You say that, okay, without any losing the max values, let's pick the maximum value of these 4. Let's pick the maximum value of these 4, and so on and so forth. So we use convolution part, conv2D part, to have several filters. We use this one to downsampling to reduce the number of, right? So that is why. But still, I didn't answer your question for that. It was 28 by 28, why it became 26 by 26. But now you can understand why 26 by 26 converted to 30 by 30. Ask you something, guys. What is this? Is it going to half the size or 1 or a quarter? Quarter, right? Look at this. How many do we have here? 16. How about this one? So it's going to be quarter, right? 1 for 25% of it. And it applies to that. So imagine that we have 26 by 26. Calculate the number. So 26 times 26. And we are gonna divide it by 13, again divided by 13, so it's gonna be 4. Does that make sense? Okay, we are gonna get to that further.
Sort of its original size, but the features can still be maintained. So the previous image, after being filtered and then max pooled, could look like this. The image on the right is 1/4 the size of the one on the left, but the vertical line features were maintained, and indeed they were enhanced. So where do these filters come from? That's the magic.
Just one thing, guys, do you feel any missing information in the right side? Well, definitely the resolution is not as best as the left side, but is this the intention of having that? We want to make the features that we are searching for kind of bolder, right? More, I mean, is it easier to recognize those features like vertical lines, as one of our team members said?
So where do these filters come from?
That's your question again, where these filters come from, and you ask.
That's the magic of a convolutional neural network. They're actually learned. They're just parameters like those in the neurons of a neural network that we saw in the last video. So as our image is fed into the convolutional layer, a number of randomly initialized filters will pass over the image. The results of these are fed into the next layer, and matching is performed by the neural network. And over time, the filters that give us the image outputs that give the best matches will be learned, and the process is called feature extraction. Here's an example of how a convolutional filter layer can help a computer visualize things. You can see across the top row here that you actually have a shoe, but it has been filtered down to the sole and the silhouette of a shoe by filters that learn what the shoe looks like. You'll run this code for yourself in just a few minutes. Now let's take a look at the code to build a convolutional neural network like this. So this code is very similar to what we used earlier, where you have a flattened input that's fed into a dense layer that in turn is fed into the final dense layer that is our output. The only difference here is that I haven't specified the input shape. That's because I'll put a convolutional layer on top of it like this. This layer takes the input, so we specify the input shape. And we're telling it to generate 64 filters with this parameter. That is, it will generate.
So now we almost know everything about it. You see that here we have 64 randomly picked filters on the frame size 3 by 3. And the next part is the frame size that we have for max is 2 by 2. The default value for the stride in here is 1. The default value for stride in max pooling is 2. So we don't touch any of those predefined parameters.
I multiply each of them across the image. Then each epoch, it will figure out which filters gave the best signals to help match the images to their labels. In much the same way it learned which parameters work best.
So the thing is, yes, we have lots of possibilities. We have lots of options among the filters, but it is going to tell us after just a few epochs that which set of filters would give us the best result. Does that make sense? So at the beginning, we are going to just randomly pick some, but some of them gives us better performance. So why not using them for the next iteration?
The max pooling to compress the image and enhance the features looks like this.
So compressed and enhanced both.
And we can stack convolutional layers on top of each other to really break down the image and try to learn from very abstract features like this. With this methodology, your network starts to learn based on the features of the image instead of just the raw patterns of pixels. 2 sleeves, it's a shirt. 2 short sleeves, it's a t-shirt. Sole and laces, it's a shoe, that type of thing. Now we're still looking at just the simple images of fashion at the moment, but the principles will extend into more complex images. You'll see that in the next video. But before going there, try out the notebook to see convolution.
Okay, the thing is, if we get to this part, that it says that note that the output width and height may differ from the input width and height. And there are 2 reasons for that. And one of them is the border effects. We saw that if we use 3 by 3, it's going to reduce by 2 the number of if it is 28, for instance, it's going to reduce it to 26. And the other thing is the use of a stride, and that was your question. So it's like if the stride is 2, then you're gonna have half the size. Look at this. Here it says that understanding the border effect. If, guys, I just simplify this one. Instead of reading, let's just go through it together. For the people at home, I need to just do it. Sorry. Let's take a screenshot and
I don't think the problem being very share the screens. You can also draw that.
oh really? I'm gonna use that. Let's just do it. So
Annotate.
this one.
Yep.
Yay! Thank you very much. Hopefully it's not gonna just leave the mark.
You can delete that.
Okay, awesome. So I haven't used that. I was always using. So, oh, I need to have it there. So look at this one. How many elements do we have? 5 by 5. Am I right? So the thing is, just see. Okay, good. I'm going to pick 3 by 3, which is going to be this one, right? And it is going to be exactly this, right? And then I'm going to move towards the index, which is going to be these 3 by 3 guys, and it's going to be exactly this one. And the last is going to be 3 by 3 like this, and it's going to be this one. Am I right? So how many pixels did we have initially here? 5. The result of this, which is going to be, I mean, the summation of all those numbers is going to be 1, 2, 3. So instead of 5, it is like 5 minus 2, which makes it 3. The same thing applies to this one. I'm going to use just one color for. So because we use this one and then we are going to use next one and then we are going to use the last, these guys are going to stay here, here, and here. So instead of having 5, it converts to have 3. So what if I want to, this is what we call it valid, the default. So whatever the size is, if you pick the 3 by 3 window for conv2d, it's gonna just convert it to what? 3 by 3 instead of 5 by 5. But what if you want to have the same size? In that case, let's just delete clear all drawing. Didn't I tell you? Thank you very much. So, and it says that if you want to get an output feature map with the same spatial dimensions as the input, you can use padding. And that padding, mostly we just have 0 padding. And you remember in the image that I showed you at the beginning. Yeah, this one, you see that we had 0. So we call this 0 padding that we have. And how it works, padding consists of adding an appropriate number of rows and columns on each side. Why didn't say that just one row on top, one row on the bottom, and one column on the left, one column on the right? Because if we are working with 3 by 3, we just need to have one on top, one on the bottom, one column on left, one column on the right. But padding consists of adding an appropriate number of rows and columns on each side of the input feature map, so as to make it possible to fit center convolution windows around every input type. So for 3 by 3, it says that it's 1. Let's just do one thing here together. Again, I added one row on top and I added one column on the left. Look at this one. Here 3 by 3 generates this one. Then the next block generates this one. The next block generates this one. Also, this green. And finally, the last block generate that. So in that case, by adding just 2 0 column and rows, we technically kept the size of the output of this as 5 as well. So if you have that, and that is what we call the feature is equal to same. This is what we call it same. Same means that keep the original size, but the default value is valid, means no zero padding, and it is going to be, so look at this one. It says that in convolution, in conv2d layer, padding is configurable. We are the padding argument, which takes 2 values. If you say valid, it means that no padding, and if you say same, it means that pad in such a way as to have an output with the same widths and same heights of the original picture that you fed in. And the padding argument default is what? Is valid. Yes, Negi?
So just to have like same, we should always have the padding.
If you want to have the same, yeah, exactly. We need to have padding. Yes.
Is there like any situation that we have like more padding, like 2 row or padding?
If your window is 5 by 5, then you need to have 2 rows on top, 2 rows on the bottom, 2 columns on the left, and 2 columns on the right. The default for 1 by 1, sorry, the default for 3 by 3 would be just adding 1 in each dimension, in each side. Could say. Does that make sense? And we normally use these two, either 3 or what do we call it? Either 3 or 5, but mostly 3. But one of the things that we already understood was the notion of strides. The notion of strides means that here we try stride equal to, oh, it doesn't work. The stride means that we didn't have stride equal to 2 till this moment, but look at this. This is the first 3 by 3. What we expected to be the next by stride 1 is this one, right? So if I had that by stride, but what if I use a stride 2, means not this one, but the next one? It's going to be this. Am I right? So in that case, this is exactly like what you see here. So not shifting just 1 block, but 2 columns. And the thing is, it's going to have, what is the benefit of having that? It's going to have a compression, but is it really the best way to compress? The answer is no. Let's just quickly read that to make sure that nothing is left. But the distance between 2 successive windows is a parameter of convolution called its stride, which the default I showed you, it's 1, but now we tried 2 as well. It says that strided convolutions are rarely used in practice. Although they can come in handy for some types of models, it's good to be familiar with the concept. The good thing about stride is what? Just downsampling. But we don't use strides in conv2d for downsampling. And it says that for downsampling, we would be better off using max pooling. And by saying that, we are ready to get the concept of max pooling. Before I continue and talk about max pooling, let's spend a few seconds, you yourself just search a little bit, see what is max pooling and what would be the benefit of using that. And a volunteer, brave volunteer would just tell me. What is max pooling? Between max pooling and okay, you're gonna talk. Is there anyone who worked on assignment number 3 or just even reviewing things? Look at it, good. So the topics that we covered today, or we are going to cover, you're fully utilized for the starting knowledge. The thing is, some of the filters that we use here and we see that come to the users, we just generate those and apply on the different images. They're very straightforward and easy to follow. I mean, the steps in this. I'm sorry, I'm not welcome. Check the notes. If I can say that, I'm gonna just sleep, so you can either talk or walk.
So I don't probably name it. So here, shouldn't be like, you're selecting like 3 by 2, right?
That is not accurate.
Yeah, so if it's like 3 by 3, then also the next one should be like. So,
Yeah, actually, I mean, blame the author that why they did it like that. I'm gonna just, it's not very accurate. I'm gonna show you the more accurate. In 2 of the videos that we're going to watch, they have better way options. And the first video, if you remember, the cat thing, it is more accurate. So any volunteer for max pooling? Okay, I'm going to define max pooling and then we are gonna eliminate this concept from convolutional neural nets and see what would happen. Is it going to impact negatively on the system, on the model or not? So again, it says that the size of the feature maps is halved after every max pooling 2D layer. To be more accurate, we could say that the size of each dimension is halved, but the overall is quarter, right? So you see that's kind of like not very accurate to say the size is half. Yes, the size of each dimension is half. The overall size is just 25% of the original. And we already know that why 28 by 28 became 26 by 26 first, and then why it became 13 by 13. And we calculated that a few seconds ago that the result is 1/4 or 25% of it. And then it says that that's the role of max pooling. Max pooling consists of extracting windows from the input feature maps and outputting the max value of each channel. Do you remember the gentleman said, and I told you that here the frame that we are talking is what is, yes, 2 by 2 in the video. And the stride is 2. It doesn't go to the next column, but 2 columns after that. Lovely. So they are transformed via a hard-coded max tensor operation. And a big difference from convolution is that max pooling is usually first. That's one of the problems. Is done in 2 by 2 window. That's the first thing. While the convolution is 3 by 3. And it is 2 by 2 and the stride is 2 for what? For down sampling to reduce the size. You saw that it was 4 by 4, 16 units, and it became 2 by 2, which is going to be 4 units. Yep. Yes. Yeah.
And then for the others, when we have then that was like
It is because of conv2d, and that's because we didn't have padding on the sides, right? Yes, it is possible, but there's no guarantee. Hmm.
function like
Oh. Now look at this one. The functionality of conv2d is applying different filters. If you say that, okay, just go to the next column, whether you want it or not, you're gonna reduce the role of one column unintentionally. But if you get by stride number 1, if you get the result of the output, and you're gonna have output feature map, and you fit it into max polling, it's going to say, okay, I got it, I got a picture, don't worry, I'm gonna just reduce the size in 25% of it and just intensify on the features that you very much want to see. Okay, it takes a few maybe times to review and just get it better, but look at this one. It says that, okay, you know what, forget why using this one, let's only have conv2d and no max pooling. And look at the result. Here, this is the architecture. We have these number of parameters and the overall number of parameters. And it says what is wrong if we do not have max pooling and we just rely on conv2d. Do you remember that I said at the beginning of the session, and I think that still we can find the drawing somewhere, that I said, yes, there we go. I said, if we have number 6 somewhere, it doesn't matter in conv2d if it is on the left side, right side, center, or wherever it is. As long as we can find those features, Rachel, like having, for instance, look at this one. We have one kind of diagonal line here. We have one curvy thing here. One curvy here. As long as we could find those features anywhere, awesome. So now the question is, if we just use max pooling, read this part carefully in the book. It says that, I'm gonna tell you, and later we're gonna read it together. If we are in a window of 3 by 3 without any max pooling, this 3 by 3 window has the information of 7 by 7 2 layers before. So what's wrong with it? We want to get the info of here, make it small, toss it to the next person, go to the next, make it small, toss it to the next, compress it, toss it to the next layer, compress it, toss it to the next layer. So in that case, you're gonna have a kind of compressed layer that this guy has a flavor of this place. And you go further and do that conv2d max pooling, conv2d max pooling. It's like, get the feature of that, right? Scramble it, pass it to the next, scramble it, pass it to the next. So after a few layers in here, you're gonna have a flavor of something that you had on the other side. Long story short, you don't need to have one specific feature the way that we had it in densely connected layers in one part of the screen. If you can fetch that in any location of the screen, you're good. Does that make sense? Let's read that. Guys, this chapter doesn't have that much programming things, but understanding these tiny, teeny things is a bit challenging. So don't get disheartened that, oh, Reza, I read it and I couldn't get the whole concept. in the first attempt. Let's read this. It says that it is conducive to learn a special hierarchy of features, and the 3x3 windows in the third layer will only contain information coming from 7x7 windows in the initial inputs. Now we know why, because we don't have that compression passing to the next, compression passing to the next. In that case, the high-level pattern learned by the ConvNet will still be very small with regard to the initial input, which may not be enough to learn to satisfy digits. Try recognizing a digit by only looking at it, through windows that are 7x7 pixels. So we need that features from the last convolution layer to contain information about the totality of the input. Guys, totality of the input cannot be achieved by only using conv2d. Right? Just read this part. After 2 layers, if you have 3x3 window, it has just a little bit bigger window. It doesn't have any idea about the other side of the picture. The next thing is, imagine that we don't have max pooling. The number of parameters after that is going to become 15 million.8, which is crazy. The number of things that we had before using max pooling was 30K. Imagine that, what a big burden on the shoulder of processor to just deal with. So in short, the reason to use downsampling is to reduce the number of feature map coefficients to process, as well as to induce the spatial filter hierarchies by making successive convolution layers look at the increasingly large window. So one of the thing is, max pooling isn't the only way to achieve downsampling. Stride is the other one, but it says that the best is not to use stride. The other thing is, why we use max pooling, not average pooling, for example, or not min pooling? Why we used max pooling? Any idea? Sorry? Let me ask you one thing, Nigel. If we say average, it's going to tell us what? Not very important things. Whenever you, for instance, you're asking ChatGPT, hey, summarize this paragraph and give me the most important 20% of the gist of the paragraph, right? It's not going to bring you the random average words. It's going to focus on the important features, right? So the simplest answer is they tried all those things, and actually you're gonna see that they didn't put it aside completely. We have algorithms that they use average pooling instead of max pooling. But in general, max pooling is the best, is to go kind of thing. You had a question, Prakash. Oh, please, just
Basically, when you go with the maximum character of something, it will give you a more accuracy and then an average. Suppose if you are talking about like a line, and that line is basically, if you having an average of that line, if something like a linear going on, and if you have an average of it, you will just get the gesture of it, not the in like a maximum characteristic of something. So that's why we go with the maximum. Maximum will give you a more information about something as compared to the average one.
let me tell you my understanding from what you said. The more important part of the information would be get more credit, right? when we say max, means that, okay, just bring the most valuable sectors of the data. Let's read this one. It says that, but max pooling tends to work better than these alternative solutions. While we still have them, nobody said that you're not allowed to use other types of pooling, but these guys are better things. So it's important, more informative to look at the maximal presence of different features than at their average presence. And by saying that, I quickly go through the things that we want to cover in the coming session. And after that, we are gonna enjoy watching the 2-3 presentations. We pause it once in a while and intensify the concept. We try to understand more. The next week, we are gonna work on a data set that you need to, upload to the Colab. It's not like one of the default Keras data sets, like Reuters and so on. The data set has come from Kaggle competition. If I can find the source, it was somewhere around here. Yes, there we go. So that's the Kaggle. I have downloaded and I have even chopped it into the original data set contained 25,000 pictures, 12,500 pictures of cats, and the same for dogs. So it's very balanced. So the best metrics for such a thing is accuracy, because the data set is balanced. But we are going to fetch just 4,000 pictures, 2,000 cats, 2,000 dogs, and we're going to use 1,000 cats, 1,000 dogs, totally 2,000 for the training part, and we're going to pick 1,000 for the validation and 1,000 for testing. Lovely, yeah. The funny thing is, compared to the result that they got in 2013, just by applying a very normal ConvNet, we are going to get to a 71% accuracy, which is quite good, reasonable. And then we are going to use a technique called data augmentation. And data augmentation means that, imagine that you have just Reza's picture looking 90 degrees to the camera. So if you just want to rely on my picture like that, what if I tilt my head? What if I just do this, or I zoom out or zoom in? You know, we cannot, just find all this. We are gonna artificially create 10 pictures out of just the current picture that we have in hand. So we call it augmentation. And with that trick from 71, we are gonna get to the percentage that you see here, 82%. That's crazy. In just one trick, we are gonna increase 11%. The next thing to know is, guess what? Imagine that you have a model already trained by kitchen stuff like cutleries, right? So your model is already trained based on the kitchen stuff. Imagine that you bring that model to something totally different, which is called, for instance, cat and dog. It's going to help you a lot. So the other trick is feature extraction with a pre-trained network. It is going to work pretty fine. And the last one is to fine tuning, which is, you're gonna see fine tuning a pre-trained network, right? And with these strategies, we can get to 97% accuracy, which is just crazy compared to the 2013's competition. Our accuracy with less than 10% of the original data is even higher than that, right? So we are going to see the importance of all these things. And let's just quickly review. If I missed any part. At this point, the will be okay. So because we have limited number of data, guys, what is the problem that we have in data sets that we do not have very much records or pictures?
Trained, they don't understand their,
Excellent. They won't be accurate. And what is the major problem when we have limited number of rows and number of samples? Sorry? Okay, let me tell you my interpretation from underfitting and correct me. Underfitting means that we have capability of getting high accuracy, but we are not there yet. When we have limited number of samples, the model that we create, whether we want it or not, is very much biased towards the samples that we have and cannot be generalized. So it's going to be overfit because it is very much aligned with the samples that we have. And it does the best that it can do, but with a limited number of samples. Does that make sense? So the problem is not optimization there. The problem is generalization and when we have those problems, it's the point of overfitting. And so it says that by using data augmentation, you'll improve the network to reach an accuracy. And for applying deep learning, a small data sets, we are going to use a model which was trained by totally different data set. And then we are going to do fine tuning and we're going to talk about what is fine tuning. But the first question is, what is the meaning of limited number of pictures? Is it a few hundreds or what? Even with a few hundred pictures, you can have a decent result by applying those things. So one of the things says that one fundamental characteristic of deep learning is that it can find interesting features in the training data on its own without any need for manual feature engineering. And this can only be achieved when lots of training examples are available. But what about when we don't have such a possibility? It is possible to train a convnet to solve a complex problems with just a few tens of samples, but sorry, we can't, it is not possible, but even with a few hundred, as I mentioned a few seconds ago, a few hundred could be suffice. Says that can potentially suffice if the model is simple and well regularized and the task is simple. Because convnet learned local translation invariant features, they are highly data efficient on perceptual problems. Guys, what is translation invariant? Did I explain it in the previous part? Okay, what is translation invariant? Means that the cat is exactly that. How can I tell people at home, guys? Somebody just imagine that we have a cat head and the cat is going to just change the degree of the head, right? So means that I can recognize no matter how cat pose in front of the camera. I can recognize it, and that's the actual way that we recognize the things. And it says that training in convnet from scratch on very small image data set will still yield reasonable results despite a relative lack of data without the need for any custom feature engineering. What can you understand from this sentence? It says that deep learning models are by nature highly repurposable. What are the things that we learn from models? Models are nothing but a set of weights and biases that they are adjusted based on the samples that they have. If you start from the scratch, they're gonna just use random values that could be totally off. But if you try to use a kitchen stuff data set, still it has some valuable weights and biases that they are not randomly assigned. They are based on some pictures. So that is why. And next week, we are gonna start, just remember, because we want to use it several times, this time we are not gonna drag and drop. It takes forever if we drag and drop the pictures. We need to have our Google Drive ready for such operation. And we're gonna work on that next week. But by saying that we are ready for these videos, still we have lots of things to do. Don't worry. Okay, so what is this in the class? Okay, this one. This is a good video. Don't worry, anytime that anyone wants to, you have the videos, guys, for those who have some other priorities. You can just watch these videos at your convenience, but I'm going to you're gonna watch this one, almost 9 minutes, and only this one, 37 minutes, and this one, which is 32 minutes. So we're gonna finish almost 3 point something. Why are you laughing? Serious. Look at this one. This is super important.
In this video, we'll be discussing convolutional neural networks. A convolutional neural network, also known as a CNN or ConvNet, is an artificial neural network that has so far been most popularly used for analyzing images. Although image analysis is the most widespread use of CNN, they can also be used for other data analysis or classification problems as well. Most generally, we can think of a CNN as an artificial neural network that has some type of specialization for being able to pick out or detect patterns and make sense of them. This pattern detection is what makes CNN so useful for image analysis. So if a CNN is just some form of an artificial neural network, what differentiates it from just a standard multi-layer perceptron or MLP? Well, a CNN has hidden layers called convolutional layers, and these layers are precisely what makes a CNN, well, a CNN. Now, CNNs can and usually do have other non-convolutional layers as well, but the basis of a CNN is the convolutional layers. All right, so what do these convolutional layers do? Just like any other layer, a convolutional layer receives input, then transforms the input in some way, and then outputs the transformed input to the next layer. With a convolutional layer, this transformation is a convolution operation. We'll come back to this operation in a bit. For now, let's look at a high-level idea of what convolutional layers are doing. As mentioned earlier, convolutional neural networks are able to detect patterns in images. More precisely, the convolutional layers are able to detect patterns. Well, actually, let's be a little more precise than that. With each convolutional layer, we need to specify the number of filters the layer should have. And we'll speak technically about what a filter is in just a few moments. But for now, understand that these filters are actually what detect the patterns. Now, when I say that the filters are able to detect patterns, what precisely do I mean by patterns? Well, think about how much may be going on in any single image. Multiple edges, shapes, textures, objects, etc. So one type of, quote, pattern that a filter could detect could be edges in images. So this filter would be called an edge detector, for example. Some filters may detect corners, some may detect circles, others squares. Now, these simple and kind of geometric filters are what we'd see at the start of our network. The deeper our network goes, the more sophisticated these filters become. So in later layers, rather than edges and simple shapes, our filters may be able to detect specific objects like eyes, ears, hair or fur, feathers, scales, and beaks even. And in even deeper layers, the filters are able to detect even more sophisticated objects like full dogs, cats, lizards, and birds. To understand what's actually happening here with these convolutional layers and their respective filters, let's look at an example. So say we have a convolutional neural network that's accepting images of handwritten digits, like from the in this data set. and our network is classifying them into their respective categories of whether the image is of a 1, 2, 3, etc. Let's now assume that the first hidden layer in our model is a convolutional layer. As mentioned earlier, when adding a convolutional layer to the model, we also have to specify how many filters we want the layer to have. A filter can technically just be thought of as a relatively small matrix for which we decide the number of rows and number of columns that this matrix has. And the values within the matrix are initialized with random numbers. So for this first convolutional layer in this example of ours, we're going to specify that we want the layer to contain one filter of size 3 by 3. Now, when this convolutional layer receives input, the filter will slide over each 3 by 3 set of pixels from the input itself until it's slid over every 3 by 3 block of pixels from the entire image. This sliding is actually referred to as convolving. So really, we should say that the filter is going to convolve across each 3 by 3 block of pixels from the input. To actually illustrate this, I'm going to use an example that Jeremy Howard used in one of his lectures for Fast AI. This example really gave me a lot of insight behind what was going on within a convolutional layer, so I'd like to share that with you all too. I've also linked to his lecture in the description of this video. So here we have our matrix representation of an image of a 7 from the MNIST data set. The values in this matrix are the individual pixels from the image. All right, so this is our input, and this input will be passed to a convolutional layer. As just discussed, we've specified this layer to only have one filter, and this filter is going to convolve across each.
Okay, just one quick question, guys. You can look at the original image on the left side, and you can see after applying conv 2D, right, on the right side. First thing first, the first question. What is the type? Is it valid or is it the same? Sorry? Same. If it is the same, the size of these two should be similar. They are not similar, actually. The size of this, we don't have that rows here. We don't have that column here, right? So it's just one row less on top, one row less on the others. And the other thing that I want you to just consider is, do you see the values here? If you just see precisely, we can see the range here is between 0 to 1, right? And we just go through the frames, right? Like 3 by 3, and after applying that, we get to the right side. What is the range that you can see here? Between 0 to, we have 5, we have 6. Well, technically we have 5 here. You see that 5 point something. Long story short, the range is going to be drastically higher. The gentleman who explained in the first video, sorry, the second video, divided by 9, you remember? Here we didn't do that. So it means that you can just do the normalizing later. It's not something that is mandatory for conv 2D. Just, I wanted to review those things.
By 3 block of pixels from the input. So here's our 3 by 3 filter of random numbers here. When the filter first lands on the first 3 by 3 block of pixels, the dot product of the filter itself with the 3 by 3 block of pixels from the input will be computed and stored. This will occur for each 3 by 3 set of pixels that the filter convolves. So look, we would just take the dot product of the filter here with this first 3 by 3 block, and then we'd store it over here. Now we slide to the next 3 by 3 block, take the dot product, and then store the value here. If we look at the formula for each of these cells, we can see that it is just indeed the dot product of the filter with each 3 by 3 set of pixels from the input. So here we have this first value is the dot product of this input with this filter. And then if I click on another random value over here, we can see that this value is the dot product of the filter with this input. So after this filter,
Do you see the beauty of what he has done? They have done just something like the heat map sort of thing. So the values that they contain 0, you see, they are totally white, and those that close to 1, they are saturated by red, and we have similar things on the other side. And everything is done manually, just calculating using Excel. Actually, what you need to do, guys, did you see this one? For those who want to go through the assignment number 3, it's exactly like doing these steps instead of using Excel, right? Just doing it in a for loop or something inside Python.
We'll be left with a new representation of our input, which is going to be made up of the entire matrix of those stored dot products we got from the filter. This matrix of dot products is going to be the output of this layer and is represented here. This is what will then be passed to the next layer as input. And this same process that we just went through with the filter will happen to this new output with the next layer's filters. Now, this was just a very simple illustration, but as mentioned, we can think of these filters as pattern detectors. So we can't really observe any specific pattern that was picked out from our filter in the example we just looked at in Excel. But let's show our original image of the 7 here. And now let's say we have 4 3x3 filters for our convolutional layer. And these filters are filled with the values you see here. And these values can be represented visually as these filters where the -1s correspond to black, 1s correspond to white, and 0s correspond to gray. So if we convolved our original image of a 7 with each of these 4 filters individually, this is what the output would look like for each filter. We can see that all 4 of these filters are detecting edges. In the output, the brightest pixels can be interpreted as what the filter has detected. So this first one we can see detects top horizontal edges of the 7, and that's indicated by the brightest pixels here. The second detects left vertical edges, again being displayed with the brightest pixels. The third detects bottom horizontal edges, and the fourth detects right vertical edges. Now these filters are really basic and just detect edges. These are filters we may see towards the start of our network. More complex filters would be located deeper in the network and would gradually be able to detect more sophisticated patterns like the one shown here. We can see the shapes that the filters on the left detected from the images on the right. This one here detects circles, and this one at the bottom is detecting corners. And as we go even further into our layers, the filters are able to detect much more complex patterns, like these dog faces being interpreted in this filter, or even the bird legs detected in this one. All right, so now if you're interested in seeing how to work with CNNs in code, then check out the CNN and fine-tuning videos in my Keras Deep Learning playlist. So I hope that
The next thing that we're going to watch would be this one, the 22 minutes of this.
subclass layer.
So the first question that comes out, of course, is that whenever you see machine learning or you hear about.
Just give you a heads up, guys. Since day 1, we have gone through simple density layer networks. It took 4 separate chapters, and then we get to come to in this 22 minutes that we're going to watch, the gentleman started from 0 to exactly here, which is going to covering the conv 2D as well. So it's a good review. Let's just do it together.
Machine learning, it seems to be like this magic wand. Your boss says, put machine learning into your application. Or if you hear about startups, they put machine learning into their pitch somewhere and suddenly they become like a viable company. But what is machine learning? What is it really all about? And particularly for coders, what's machine learning all about? Actually, quick show of hands, and many of you are coders. Yes, I know, I guess pretty much all of us, right, are coders. I do talks like this all the time. And sometimes I'll ask how many people are coders and 3 or 4 hands show up. So it's fun that we can geek out and show a lot of code today. So I want to talk about what machine learning is from a coding perspective by thinking a scenario. Can you imagine if you were writing a game to play rock, paper, and scissors? And you wanted to write something so that you could move your hand as a rock, a paper, or a scissors. The computer would recognize that and be able to play that with you. Think about what that would be like to actually write code for. You know, you have to pull in images from the camera, and you have to start looking at the content of those images and how to tell the difference between a rock and scissors, or how would you tell the difference between a scissors and a paper? That would end up being a lot of code you would have to write, and a lot of really complicated code. And not only the difference in shapes, think about the difference in skin tones, and male hands and female hands, large hands and small hands. You know, people with gnarly knuckles like me and people with nice smooth hands like Carmel. And so how is it that you would end up being able to write all the code to do this? And it's really, really complicated and ultimately not very feasible to write. And this is where we start bringing machine learning into it. This is a very simple scenario, but you can think about there are many scenarios where it's really difficult to write code to do something, and machine learning may help in that. I always like to think of machine learning in this way. Think about traditional programming. And in traditional programming, something that has been our bread and butter for many years, all of us here were coders. You know, what it is that we think about expressing something, expressing rules in a programming language like Java or Kotlin or Swift or C++. And those rules generally act on data, and then out of that we get answers. Like in rock, paper, scissors, the data would be an image, and my rules would be all my if thens, looking at the pixels in that image to try and determine if something is a rock, paper, or scissors. Machine learning then turns this around, it flips the axes on this. And if we say, hey, instead of thinking it this way, where it's like we have to think about all of these rules, and we have to write and express all of these rules in code, what if we could provide a lot of answers, and we could label those answers? And then have a machine infer the rules that match one to the other. So for example, in something like a rock, paper, and scissors, we could say, you know, these are the pixels for a rock, and this is what a rock looks like. And we could get hundreds or thousands of images of people doing a rock. So we get diverse hands, diverse skin tones, those kind of things. And we say, hey, this is what a rock looks like, this is what a paper looks like, and this is what a scissors looks like. And if a computer can then figure out the patterns between these, and can be taught and it can learn what the patterns are between these. Now we have machine learning. Now we have an application, we have a computer that has determined these things for us. So if we take a look at this diagram again, and if we look at this again, and we replace what we've been talking about by us creating rules, and we say, okay, this is machine learning, we're going to feed in answers, we're going to feed the data, and the machine is going to infer the rules. What's that going to look like at runtime? How can I then run an application that looks like this? So this we're going to call the training phase. We've trained what's going to be called a model on this, and that model is basically a neural network. And I'm going to be talking a lot about neural networks in the next few minutes. But what that neural network is, you know, we're going to wrap that, we're going to call that a model, and then at runtime, we're going to pass in data, and it's going to give us out something called predictions. So for example, if I trained it on lots of rocks, lots of papers, and lots of scissors, and then I'm going to hold my fist up to a webcam, it's going to get the data of my fist, and it's going to give back what we like to call a prediction. That'll be something like, hey, there's an 80% chance that's a rock, there's a 10% chance it's a paper, and 10% chance it's a scissor, something like that. So a lot of the terminology in machine learning is a little bit different from traditional programming. We're calling it training rather than coding and compiling. We're calling it inference, and we're getting predictions out of inference. So when you hear us using terms like that, that's where it all comes from. It's pretty similar to stuff that you've been doing already with traditional coding, it's just slightly different terminology. So I'm going to kick off a demo now where I'm going to train a model for rock, paper, and scissors. The demo takes a few minutes to train, so I'm just going to kick it off before I get back to things. So I'm going to start it here, and it's starting, and as it starts to run, I just want to show something as it goes through. So if you can imagine a computer, I'm going to give it a whole bunch of data of rock, paper, and scissors, and I'm going to ask it to see if it can figure out the rules for rock, paper, and scissors. So any one individual item of data I give to it, there's a 1 in 3 chance it gets it right first time. If it was purely random, I said, what is this? There's a 1 in 3 chance it would get it correct as a rock. So as I start training, that's one of the things I want you to see here is the accuracy, that like the first time through this, the accuracy was actually, it was exactly 0.333. Sometimes when I run this demo, it's a little bit more. But the idea is once it started training, it's getting that random. It's like, okay, I'm just throwing stuff at random. I'm making guesses of this. And it was like 1 in 3 right. As we continue, we'll see that it's actually getting more and more accurate. The second time around, it's now 53% accurate. And as it continues, we'll get more and more accurate. But I'm going to switch back to the slides and explain what it's doing before we get back to see that image. Can we go back to the slides, please? Okay. So the code to be able to write something like this looks like this. This is a very simple piece of code for creating a neural network. And what I want you to focus on, first of all, are these things that I've outlined in the red box. So,
is there anything that we are not familiar with here? The only thing is we didn't use any matrix for just watching the measurement of the. And we understand that if you don't use it, it's gonna be by default accuracy, right?
So these are the inputs to the neural network and the outputs coming from the neural network. So I love talking about neural networks at I/O because it's I/O input output, and you'll see I talk a lot about inputs and outputs in this. So the input to this is the size of the images. All of the images that I'm going to feed to the neural network of rocks, papers, and scissors are 150 square, and they're 3 by color depth, and that's why you say 150 to 150 by 3. And then the output from this is going to be 3 things, and because we're classifying for 3 different things: the rock, the paper, and scissors. So always when you're looking at a neural network, those are really the first things to look at. What are my inputs? What are my outputs? What do they look like? But then there's this mysterious thing in the middle, where we've created this CF.keras, the layers are dense, and there's a 512 there. And a lot of people wonder, well, what are those 512 things? Well, let me try and explain that visually. So visually, what's going on is, well, those 512 things are in the center of this diagram. Consider them to be 512 functions, and those functions all have internal variables, and those internal variables are just going to be initialized with some random states. But what we want to do is, like, when we start passing the pixels from the images into these, we want them to try and figure out what kind of output, based on those inputs, will give me the desired output at the bottom. So function 0 is going to grab all those pixels, function 1 is going to grab all those pixels, function 2 is going to grab all those pixels.
What I like about the presentation, what is different with what we talked before, is we always said that the inner layer, for example, here, that those 512 neurons, or we call them activations and so on. This gentleman said that they are functions, and the responsibility of them is to getting those pixels and bringing them to one of the meaningful output that we expect, whether scissor, paper, or rock, right?
And if those pixels are the shape of a rock, then we want the output of function 0, 1, and 2, all the way up to 511, to be output into the box on the left at the bottom, to stick a 1 in that box. And similarly for paper, you know, if we say, okay, when the pixels look like this, we want your outputs of F0, F1, and F2 to go to this box. And that's the process of learning. So all that's happening, all that learning is, when we talk about machine learning, is setting those internal variables in those functions so we get that desired output. Now, those internal variables, just to confuse things a little bit more, in machine learning parlance, tend to be called parameters. And so for me as a programmer, it was hard at first to understand that, because for me, parameters are something I pass into a function. But in this case, when you hear a machine learning person talk about parameters, those are the values inside those functions that are going to get set and going to get changed as it tries to learn how I'm going to match those inputs to those outputs. So if I go back to the code and try to show this again in action. Now remember my input shape that I spoke about earlier on, the 150 by 150 by 3. Those are the pixels that I showed in the previous. I simulated them here with gray boxes, but those are the pixels that I showed in the previous diagrams. My functions now is that dense layer in the middle, those 512. So that's 512 functions randomly initialized or semi-randomly initialized that I'm going to try to train to match my inputs to my outputs. And then of course the bottom, those 3 are the 3 neurons that are going to be my outputs. And I just said the word neuron for the first time, but ultimately what when we talk about neurons and neural networks is that, you know, it's not really anything to do with the human brain. It's a very rough simulation of how the human brain does things. And these internal functions to try and figure out how to match the inputs to the outputs, you know, we call those neurons. And on my output up there, like those 3 at the bottom are also going to be neurons too. And that's what lends the name neural networks to this. It tends to sound a little bit mysterious and special when we call it like that. But ultimately, just think about them as functions with randomly initialized variables that over time, we're going to try to change the value of those variables so that the inputs match our desired outputs. So then there's this line, the model.compile line. And what's that going to do? That's a kind of fancy term. It's not really doing compilation where we're turning code into bytecode as before. But think about the 2 parameters to this. These are the most important parts of learning machine learning. These are the loss and the optimizer. So the idea is the job of these 2 is, remember earlier on I said it's going to randomly initialize all those functions. And if they're randomly initialized and I pass in something that looks like a rock, there's a 1 in 3 chance it's going to get it right as a scissors or as a rock or a paper with scissors. So what the loss function does is it measures the results of all the thousands of times I do that. It figures out how well or how badly it did. And then based on that, it passes that data to the other function, which is called the optimizer function. And the optimizer function then generates the next guess, where the guess is set to be the parameters of those 512 little functions, those 512 neurons. And if we keep repeating this, we'll pass our data in, we'll take a look, we'll make a guess, we'll see how well or how badly we did. Then based on that, we'll optimize and we'll make another guess and we'll repeat until our guesses get better and better and better. And that's what happens in the model.fit. Here you can see I have model.fit where epochs, depending on how you pronounce it, is 100. All it's doing is doing that cycle 100 times. For every image, take a look at the parameters, fit those parameters, take a guess, measure how good or how bad you did, and then repeat and keep going. And the optimizer then will make it better and better and better. So you can imagine the first time through, you're going to get it right roughly 1 in 3 times. Subsequent times, it's going to get closer and closer and closer and better and better. Okay. Now, those of us who know a little bit about images and image processing go, okay, that's nice, but it's a little naive. I'm just throwing all of the pixels of the image, and maybe a lot of these pixels aren't even set, into a neural network and having it try to figure out from those pixel values. Can I do it a little bit smarter than that? And the answer to that is yes. And one of the ways that we can do it a little bit smarter than that is using something called convolutions. Now, convolutions is a convoluted term, excuse the pun.
Let's look at this one in 11 minutes and 44 seconds. We started from very scratch all the way to convolutional neural nets. You see exactly the kernel matrix that you see in the middle and just multiplications.
The idea behind convolutions is if you've ever done any kind of image processing, the way like you can sharpen images or soften images with things like Photoshop, it's exactly the same thing. So with a convolution, the idea is you take a look at every pixel in the image. So for example, this picture of a hand, and I'm just looking at one of the pictures on the pixels on the fingernail. And so that pixel is like value 192 in the box on the left here. So if you take a look at every pixel in the image and you look at its immediate neighbors, and then you get something called a filter, which is the gray box on the right, and you multiply out the value of the pixel by the corresponding value in the filter, and you do that for all of the pixel's neighbors to get a new value for the pixel. That's what a convolution is. Now, many of us, if you've never done this before, you might be sitting around thinking, why on earth would I do that? Well, the reason for that is that when finding convolutions and finding filters, it becomes really, really good at extracting features in an image. So let me give an example. So if you look at the image on the left here, and I apply a filter like this one, I will get the image on the right. Now, what has happened here is that the image on the left, I've thrown away a lot of the noise in the image, and I've been able to detect vertical lines. So just simply by applying a filter like this, vertical lines are surviving through the multiplication of the filter. And then similarly, if I apply a filter like this one, horizontal lines survive. And there are lots of filters out there. They can be randomly initialized and they can be learned that do things like picking out items in an image like eyes or ears or fingers or fingernails and things like that. So that's the idea behind convolutions. Now the next thing is, okay, if I'm going to be doing lots of processing on my image like this, and I'm going to be doing training, and I'm going to have like hundreds of filters to try and pick out different features in my image, that's going to be a lot of data that I have to deal with. And wouldn't it be nice if I could compress my images? So compression is achieved through something called pooling. And it's a very, very simple thing. And sometimes it seems a very complex term to describe something simple. But when we talk about pooling, I'm going to apply, for example, a 2x2 pool to an image. And what that's going to do is it's going to take the pixels 2x2. Like if you look at my left here, if I've got 16 simulated pixels, I'm going to take the top 4 in the top left-hand corner. And of those 4, I'm going to pick the biggest value. And then the next 4 in the top right-hand corner, of those 4, I'll pick the biggest value, and so on and so on. So what that's going to do is effectively throw away 75% of my pixels and just keep the maximums in each of these 2x2 little units. But the impact of that is really interesting when we start combining it with convolutions. So if you look at the image that I created earlier on, where I applied the filter to that image of a person walking up the stairs, and then I pull that, I get the image that's on the right, which is 1/4 the size of the original image. But not only is it not losing any vital information, it's even enhancing some of the vital information that came out of it. So pooling is your friend when you start using convolutions, because if you have 128 filters, for example, that you apply to your image, you're going to have 128 copies of your image, you're going to have 128 times the data, and when you're dealing with thousands of images, that's going to slow down your training time really fast. Well, pooling then really speeds it up by shrinking the size of your image. So now when we want to start learning with a neural network, now it's a case of, hey, I've got my image at the top. I can start applying convolutions to that. Like, for example, my image might be a smiley face, and one convolution will keep it as a smiley face. Another one might keep the circle outline of the head. Another one might kind of change the shape of the head, things like that. And as I start applying more and more convolutions to these and getting smaller and smaller images, instead of me now having a big fat image that I'm trying to classify, that I'm trying to pick out the features of to learn from, I can have lots of little images highlighting features in that. So for example, in rock, paper, scissors, my convolutions might show in some cases 5 fingers or 4 fingers and a thumb, and I know that that's going to be a paper, or it might show none, and I know that's going to be a rock. And it then begins to make the process of machine learning these much, much simpler. So to show this quickly, I've been putting QR codes on these slides, by the way. So I've open sourced all the code that I'm showing here and we're talking through. And this is a QR code to a workbook where you can train a rock, paper, scissors model yourself. But once we do convolutions, and earlier in the slide you saw I had multiple convolutions moving down, and this is what the code for that would look like. I just have a convolution layer followed by a pooling, another convolution followed by a pooling, another convolution followed by a pooling, etc., etc. So the impact of that, remember, first of all, at the top, I have my input shape and I have my output at the bottom, where the density is.
Can you please spend a few seconds, just go through all these lines of code? Is there anything that we don't know? There's just one that we know, but we haven't used it. Drop out. But the rest is totally fine, okay?
So I'm going to switch back to the demo now, see if it's finished training. And we can see it. So we started off with 33% accuracy, but as we went through the epochs, I just did this one, I think, for 15 epochs. It got steadily and steadily and steadily more accurate. So after 15 loops of doing this, it's now 96.83% accurate. So as a result, we can see using these techniques, using convolutions like this, we've been actually able to train something in just a few minutes to be roughly 97% accurate at detecting rock, paper, and scissors. And if I just take a quick plot here, we can see this is a plot of that accuracy, the red line showing the accuracy when we start.
So where should we stop? First thing first, do you think that's a kind of normal graph? Don't you see that we have a kind of peak here in epoch number 1, then we go down, then we go up. This is the validation, the blue one is the validation. And then technically what we can understand is almost in epoch number 12, that's the best. So we shouldn't rely on the random drop that happens in the middle of the road. But why we have that kind of high fluctuated graph? Do you have any idea? The one who learned everything thoroughly from beginning of the book can answer it.
Because training the random data. Yes. So basically, so it starts like layering with like less data. And it's just goes up. So I think basically it's because of less data. Like yeah, it learned like less like in each
Maybe they had some impact. But do you remember this graph? It was the result of having 4 units in the dense layer, right? Do you remember when we changed that drastically to something crazy like 512? It was like this, right? And getting back to the video shows that this one has 512. You remember that? 512. So this is, if we just change it to something like 2 layers of 16, would be something meaningful. This one is just crazy, right? Because of 512.
Started at roughly 33%, and we're getting close to 100%. The blue line is I have a separate data set of rock, paper, scissors that I tested with, just to see how well it's doing, and it's pretty close, because I need to do a little bit of work on tweaking it. And I can actually try an example to show you. So I'm gonna upload a file, I'm gonna choose a file from my computer. I nicely named that file paper, so you can guess it's a paper. And if I open that and upload that, it's gonna upload that, and then it's gonna give me an output. And the output is 100, so you think, I got it wrong. It detected it's a rock. But actually, my neurons here, based on the labels, are in alphabetical order. So the alphabetical order would be paper, then rock, then scissors. So it actually classified that correctly by giving me a 1. So it's actually a paper. We can try another one at random. I'll choose a file from my machine. I'll choose the scissors and open that and run it. And again, paper, rock, scissors. So we see it actually classified that correctly. So this workbook is online if you want to download it, have a play with it, do classification yourself, and to see how.
The other thing that I like for your assignment number 4, which is gonna be a term project kind of thing, and you're allowed to just use any topic that you want. In the demo part, not a bad idea to just test it by using this strategy. Say that, okay, I have now these kind of pictures, and let me just fit it into and see if it predicts correctly or not, right? That's very, I mean, convenient way of presenting. Sorry.
The neural network to do this. And then once you have that model, you can implement that model in your applications, and then maybe play rock, paper, scissors in your apps. Can we switch back to the slides, please? So just to quickly show the idea of how convolutions really help you with an image. This is what that model looks like when I define this. And at the top here, it might look like a little bit of a bug at first if you're not used to doing this. But at the top here, remember we said my images coming in were 150 by 150. It's actually saying, hey, I'm going to pass out an image that's 148 by 148. Anybody know why?
Anybody know why? Do you remember that because we don't have 0 padding, it's gonna reduce the size, right?
Is it a bug? No, it's not a bug. Okay, so the reason why is if my filter was 3 by 3, for me to be able to look at a pixel, I have to throw, for me to start on the image, I have to start 1 pixel in and 1 pixel down in order for it to have neighbors. So as a result, I have to throw away all the pixels at the top, at the bottom, and either side of my image. So I'm losing 1 pixel on all sides. So my 150 by 150 becomes a 148 by 148. And then when I pull that, I halve each of the axes, so it becomes 74 by 74. Then through the next iteration, it becomes 36 by 36, then 17 by 17, and then 7 by 7. So if you think about all of these 150 squared images passing through all of these convolutions, are coming up with lots of little 7 by 7 things. And those little 7 by 7 things should be highlighting a feature. It might be a fingernail, it might be a thumb, it might be the shape of a hand. And then those features that come through the convolutions are then passed into the neural network that we saw earlier on to generate those parameters. And then from those parameters, hopefully it would make a guess, and a really accurate guess about something being a rock, paper, or scissors. So if you prefer an IDE instead of using Colab, you can do that also. I tend to really like to use PyCharm for my developments. Any PyCharm facts here? Out of interest? Yeah, nice, a lot of you. So then here's a screenshot of PyCharm when I was writing this rock, paper, scissors thing before I pasted it over to Colab, where you can run it from Colab. So PyCharm is really, really nice. You can do things like step-by-step debugging. If we can switch to the demo machine for a moment. A quick demo of PyCharm doing step-by-step debugging. So here we can see we're in rock, paper, scissors. And for example, if I hit the debug, I can even set breakpoints. So now I have a breakpoint in my code. So I can start taking a look at what's happening in my neural network code. Here I'm just saying this is where I'm preloading the data into it. And I can step through and I can do a lot of debugging to really make sure my neural network is working the way that I want it to work. It's one of the things that I hear a lot from developers when they first get started with machine learning is that there seems to be your models are very much a black box. You have all this Python code for training the model, and then you have to do some rough guesswork. With TensorFlow being open source, I can actually step into the TensorFlow code in PyCharm, like I'm doing here, to see how the training is going on, to help me to debug my models. And Carmel later is also going to show how something called TensorBoard can be used for debugging models. Can we switch back to the slides, please? So with that in mind, we've gone from like really just not understanding what, or just beginning to understand what neural networks are all about and basic hello world code, to taking a look at how we can use something called convolutions. And there's something that sounds really complicated and really difficult, but once you start using it, you'll see they're actually very, very easy to use, particularly for image and text classification. And we saw then how it was, in just a few minutes, we're able to train the neural network to be able to recognize rock, paper, and scissors with like 97, 98% accuracy. So that's just getting started. But now to show us how to actually stretch the framework and to make it real and to do really cool and production quality stuff, Carmel is going to share with us.
Okay, this is the 22 minutes that I told you. But the thing is, unfortunately, I don't want to rush, but just to show you this gentleman's face. And if you just quickly go through the things that he talk, you see that, for instance, these are, and guys, everything that he's talking about are things that we have already covered. Let me just, this is a normal neural nets, the densely layers, but what if you want to bring the concept of convolution? We talked about it, but different filters that they fetch different features and how it works and how it brings having this multiplication, giving the answer. So you see that it says that filter and we have feature map, or the best way to describe it, this is out feature map or output feature map, and this is the original feature map. And you see that these are the, it says that the input image that we have, then convolutional layers, and then we have max pooling, and after that we can just connect it to fully connected layers that we already familiar with. And again, guys, do you see the logo here? What's it? MIT University, they present it for not undergrad, they present it for grad students. So, and it's not day one or the first session, it is something like a few sessions after the beginning of the semester. So the idea behind this is these two videos. The second one, I want to get the confidence that, okay, we know, and we can just be part of the dialogue and talk, and to be aware of what is happening in such professional sessions. That's one thing. And if you want to have a presentation, for instance, somebody says that, okay, whatever you learn in data science, I want to hire you, elementary job, but I want you to tell me what you learned actually in data science. Guys, this presentation, this 20 minutes, if you have 20 minutes, that is super dope way of presenting from zero to hero. I thought about different scenarios, but I couldn't come up with any better idea. So in 20 minutes, you can say many things. And remember, in any job interview that you go, many people that like HR, they have almost zero knowledge about this. And if you can impress them, then you can target the target audience is HR. If you can just teach them something, then thank you very much. Sorry, I wanted to finish the class a little bit sooner than normal. That never happens. And I hope you enjoy it. And next week, we are going to continue hands-on practice together. Just closed. Thank you. People at home, thank you as well. Have a good one. Bye.